Did you have a read of it, Joe?
Last chapter.
Yeah, most recent. I just want to load. Right, describe and explain the process of the nuclear fission. What was the last one I did? B3, wasn't it?
Yeah.
Oh, come on. Come on. Am I doing version 2? Yeah. I just want to save the name of this so I don't forget it later. So I just did here. This was B3. Okay. What's nuclear fission? A part 1. Which one's fission? KJ, come on.
When you break into and release a neutron of energy.
Give me a proper sentence.
He's going to use his hand as an example.
The no, not this one.
Breaking of
the process of. Okay, go for it. Okay, fine. Yeah. Okay, we'll go with that. Dividing.
material.
Yeah, dividing a heavy nucleus by how? How do you divide it? How do you break it? The process of dividing a heavy nucleus by
shooting a neutron at it. Yeah.
Let's go with a slightly more physically word than shooting. Firing. By firing a neutron at it. Yeah, something like this. And this process releases a lot of energy. The marking scheme goes for. If they say shooting, I take it all back. I know, even better word than firing or shooting, bombarding. It's much better, much more physicsy. The nucleus interacts with a bombarding particle, usually a neutron, to form a compound nucleus. Compound means, broken, which then splits into, compound means the nucleus hits it, and then splits into 2 or more. Yeah, that's fine. Something like that will do fine. Right, uranium-235 can undergo fission. Explain what is meant by critical mass of uranium-235. Now, I think that's actually, I'm not even sure if that's a term on the syllabus. I want to check it. No, I don't know, because
you have that.
I could have missed it. You see, critical mass is not actually a word in the syllabus. Yeah, critical damp. We did dampen. Mm-hmm. Yeah. So. Yeah. And also, you recall I didn't talk about triple point in class before. But again, you can see that triple point is not also on the syllabus. So this is what I mean. Sometimes this happens. Yeah. Now, my students didn't have this exam last year. Maybe this went to Manchester, so I didn't notice this problem. You know what I mean? Anyways, critical mass and triple point not really there on the syllabus, but I'll give you the critical mass anyways. Basically, the critical mass is how much of the material you need for the process to work. Because if you have too little, too few, too little, too few, think back to English. Few is when it's uncountable, isn't it? Few is countable. Yeah, few is countable. So too few. Yeah. If you have too few, you won't have a chain reaction. Remember we did chain reaction where the neutrons are released. Do you remember chain reaction? The neutrons are released and they collide and they release more neutrons. So watch what happens. If you don't have enough, if you don't have enough, when the neutrons are freed, they're not likely to hit into another uranium nucleus. If you have enough, then what will happen, then when they're released, they will hit into more atoms. So, you can do it like a table, like if the mass is less than the critical value, then this will cause no chain reaction. But if the mass is greater or equal to the critical, this will cause a chain reaction. In other words, if you need to have enough nuclei so that freed neutrons are likely to collide with nearby uranium-235 nuclei. I mean, I'll give you what they have here. They said the mass of uranium must be greater than or equal to the critical mass so that there are more neutrons causing fission than there are escaping from the material. In other words, it needs to be enough mass so that the freed neutrons can collide into nearby uranium rather than just disappear off into the distance. Right, next. Is the next one just balance an equation? Fantastic. Right, so 235 uranium plus a neutron. Well, we know what the neutron is. It's 10. That becomes something up the top we don't know. 56 down the bottom plus 36 krypton plus 2 neutrons. 1 0. So actually I can see what the bottom here for uranium must be. It must be 56 plus 36. 92. Great. And the numbers on the top, can I get those? 144 and 90. How'd you get them? 144 and 90? Because it says it in the question. Barium 144 and krypton 90. Second there, I thought you were a genius. Yeah, don't worry, that didn't last long. Alright, so we're already on the B part of this question.
They gave you like one mass in the question.
Oh wait, sorry, no, there's still one part left, sorry. The fourth part here is what is the energy per nucleon of uranium if the masses of the particles are as shown. You'll need to use, okay. So in other words, they want to know what the binding energy for uranium is. Now, I think they're giving you, if you look, they're giving you more information than you need. In fact, you don't really care about what the mass of the krypton or the barium is. You do care what the mass of a neutron is, and you also care what the mass of a proton is, but I don't think he gives that to you, does he? Is it in the table book?
Yes.
don't know, he has a very long way of doing it in the book.
2.8 times 10
No. No. Let me just check one thing here. I want to see. Okay, I'm going to do it differently to how it's done in the book, the marking scheme, which I think is okay, but it means I need to use the mass of a proton. Now, the mass of the proton is not given to you in the exam, but I don't feel like it's a problem to use it because it's a constant on your calculator. Anyways, so uranium 2, 3, 5 and 92. How many protons is that? 92 protons. How many neutrons is it? 235 minus 92 is 143 neutrons. So the mass should be the mass of 92 protons plus 143 neutrons. Now, you have those on your calculator. You have the mass of a proton and the mass of a neutron on the calculator as a constant. So that would be 92 plus mass of a neutron. So if I hit that in on the calculator, I'll get 3.9339 etc. times 10 to the minus 25 kilograms. Now you should you can leave it like that if you want, that's fine. But what is the actual mass of uranium? It's given in the question, but its actual mass is 235.0439 U, which I should convert into kilograms. And the mass of the neutron is given there. But the U is also given at the start of the exam in the formula constant. So the U is... hang on, you have to tell me now in 1 second. Tekken, what is it? 1.65 Okay. Now I'll call this one here M1 and M2. Which will be bigger, M1 or M2? Correct. So the mass defect is the difference between the two. So if I just subtract them, I'll get a small number. Where did this missing mass go? It didn't just disappear. Where did it go? Yeah, energy. What type of energy? The binding energy, to bind the atom together. So if you can use this formula, you can get how much energy that is. So if I multiply this by C squared, which is 3 times 10 power 8 squared, that is 2.9 times 10 to the minus 10 joules. But he wants these in electron volts, I think. So, electron volts, if I convert, what number is the electron? 23. That's 1810422.898 electron volts, but he actually said mega electron volts. Well, I'm writing in mega electron volts now. But he doesn't want the total binding energy, he wants the binding energy per nucleon. So how can I finish this? Divide by 235. 7.7 mega electron volts, which is it's the right number, but my decimal point is in the wrong place. When I look at the answer in the book, it's like this, which means at some point I lost a number somewhere, or it's a typo here. Yeah, here. He basically has 181 at this step. So it's like I have one of these numbers too much, which means...
Here, yes.
Which one? Yeah? What do you think it is?
What's the M?
You can want.
Okay, minus.
Here, let me try. 2.9 times 10 power minus 10 divided by...
What's the M?
No. I wonder if it's a mistake here.
You can do this calculation again in calculator.
Right, let's do it really quickly. So, 92 mass of the proton is constant number 1, plus 143 mass of the neutron, which is constant number 2. And then I need to minus 235 point... Tekken, can you give me the U value? One sec. 235.0439 times, yeah, 1 point.
66 times 10 power minus 27.
Are you sure?
No.
You're right. Or maybe I typed in my value of C wrong. What's the value of C? Speed of light. It's 3 times... Yeah, 3 times 10 to the power of 8, isn't it?
Yes.
That answer is wrong.
Which one?
The M1 minus M2.
How wrong?
Well, hang on. Maybe... No, I'm getting the same answer here. 2.9 times 10 to the minus 9, and then divide by electron, which is constant number 23, divide by mega. I've just checked twice, and I've gotten the same answer at this point, 1810. So I think maybe his decimal point is wrong by 1. 1 decimal place off. Actually, you know what? This is something we can look up. Can you hit in on your phone, type in the binding energy of uranium-235. Okay, so while you're doing that, let's just have a look at the next part. Does anyone else have their phone handy? Binding energy of uranium-235. Did you get it? Anyways. Any luck, KJ? Yeah? Any luck? What's taking so long? I'm sure I could find this quicker. Yeah, what's in kilo electron volts?
178.
What is it? 17.
783,870.285 plus or minus 1.
Kilo electron volts.
Yes.
Kilo. No,
You know, like when
I'm wrong. So one of my numbers is wrong.
when you do n e is equal to mc squared,
Yeah.
you got 2.9 times 10 minus 10. Over here is like 3.57 times 10 minus 17 joules.
Here.
Like, it's like I got the same example, you know.
But what?
172 mega.
Hang on. There's a different question
What
though.
you get is this one here, they worked it out for uranium. They worked it out. How you did it?
Like how I'm doing it.
Yes.
And what did they get? 1.74 giga electron volts. Goodness. Here, hang on. Binding energy of uranium. 235, is it?
Mm-hmm.
Look, it's right here on Wikipedia.
Mm-hmm.
Oh, I'm thinking
You were looking at Wikipedia as well.
Ian got on Wikipedia, A-level physics, finding energy.
But where could I have made my decimal point mistake? Did I forget to convert something from grams to kilograms? Or?
Maybe that.
No, they're all in kilograms. Binding energy. Yeah. 1783870. Ah. No. My answer is right. So if you look at this number here, this is in kilo. So if I just hit that in on the, well, I'll just put up here, if I put that in and multiply it by 1,000, 1, 2, 3, that's it in electron volts. If I want mega electron volts, I should divide by 1,000,000. 1, 2, 3, 4, 5, 6. So I get 1783 mega electron volts. And what I got was, earlier, I got 1810. Where the true answer is 1783. So that's close enough. So in other words, my point is, at this step, I was right to have 4 digits, whereas in the marking scheme, he left out the 0 here. I think that's his mistake, not mine. Okay, so that's fine there. Yeah, noted. Right, B part 1. The half-life is 11.52 seconds. How long until an 8 remains? So how do I do that? After one half-life, how much is left? Funny enough, you're right, there's half left. And then after another half-life, 25%. And then another half-life, 12.5%, which is an 8. So the answer is 3 half-lives. (34.56 seconds).
Zero, 1/8 plus H.
No, TH. An 8. Okay, the next part. Is calculate how long until 100 is left. So we have to use our formula. Yeah.
Big.
What? 34.56. What's wrong?
It'll 11.5 seconds.
That's a half-life.
Okay.
What?
Okay.
Are you sure? Okay. Continue. Number 2. It's 3 times this. Number 2 is how long until we have a 100 left. So the amount, I'll write as a n. N equals n0 e minus t over, e minus lambda t. Do we know how much we have at the start? We don't, but we can actually do it as percentages. At the start, what percent do I have? 100%. And at the end, what do I want? 100 is 1%.
Yes.
And what's the formula for the lambda? Do you remember? Log 2 over half-life, which is 11.52. This is enough information here. Yeah. So I got, when you solve this, time is 76.54 seconds. Yeah. And then finally, what is the activity? No, after 30 seconds, yeah, so you know what it is after 30 seconds, the activity is that. So when time is 30, the activity is 6.55 kilo equals.
So
the initial one. Now, so what I should do is work out the activity at the beginning. So we have A equals A0 E minus lambda T. 6.55 kilo equals A0 E minus log 2 over 11.52 times 30. So this is enough information to get the A0. I'll check now. What did you say? No, that's not what I got for A0. No, that's way too big. I got 39.8 kilo equals. Well, let's see if I get the right answer at the end. So at the very last step, at the beginning, N0 equals, what's the rule? A equals, A equals minus lambda N0. So N0 should be just A0 divided by lambda. No, I must have had a mistake with my BQ here. Let's double check it. 6.55 times 10 to the 3 over E power minus log 2 over 11.52. Yeah, no, I got A0 is 39827 equals 398. I can't read. 39827 equals. And the formula is A equals lambda n, right?
Yes.
Or is it n equals lambda A? No, it's A equals lambda n.
Yes.
So then n is A over lambda. So divide by lambda. No, yes. Lambda is log 2 over 11.52. I got this 661913, but the answer is not this.
Is it because of minus?
Flip.
Minus?
No, I misread it. Nobody said anything to me. That number in the question, the 6.55 kilo, that's the A0.
Yes.
But I was just finding the A0. I had it backwards. It's the other way around. No, doesn't matter. Don't care. Right. So the A0 is 6.55 kilo. The lambda is log 2 over 11.52 and the T is 30. So what's the A?
That was it.
There's no Z. Where?
Yes.
2. Okay, so the A is 1077 equals. Yes, he was right. I know. I'm as surprised as you are. Yes. So the A equals lambda n. So that means lambda n equals this. So n is 1077 over lambda. And now I get the right answer. 17903. Right, B5. A B6 as well. Have a look. Closing